Alright, welcome back. This is text problem 7-45, a suggested problem for lesson 19. I'm going to try something a little different this time. If you don't already, get out a scratch piece of paper or print off a blank version of the suggested problem and follow along. So if you need to pause, go ahead and pause it and get ready. As I go through this, I'm going to ask you to pause at certain points and ask that you continue solving the problem to a certain step, and then you can unpause it and catch back up. I want to do this so that you can test yourself and see how well you're grasping some of the concepts involved in the problem. Alright, so let's get started. So the first thing we're going to do is read the problem, of course. We can see from the problem statement that we have a constant force of 122 newtons is displacing a block at a constant speed, 5 meters per second. And the problem asks us to find the rate at which the force is doing work. So that's right here at the very end. So alright, so our key indicators for this problem are the fact that we have work being done, it's being done by a constant force, and you may not realize it yet, but this constant speed is going to be important. Alright, so let's go into our draw step. Alright, our drawing is complete. We have our mass here. It's being pulled at some angle with respect to the horizontal, and it has a constant speed here. So this isn't a free body diagram per se, but it is a drawing that gives us the information we need. Alright, to continue, we have a constant force and a constant velocity. So we have to assume that there's another force, probably the force due to kinetic friction, that is equal in magnitude to the horizontal component of the applied force that is keeping the block's acceleration at 0. So if we were to separate this into our x and y components, our block isn't coming off the ground, so our acceleration in the y direction is 0, and the fact that we're moving at a constant speed horizontally means that the acceleration in the x direction is also 0. Alright, next, our task for this problem is to calculate the rate at which the applied force is doing work. So we have to calc dW dt. So let's look at the physics involved. We know we have a work problem, but that doesn't give us the rate at which the force is doing work. We have to take the first time derivative of our work function to get the rate at which the applied force is doing work. Now, do we have a formula on the PRC that has the first time derivative of our work function? Yeah, sure we do. The power is equal to the first time derivative of our work function. Now we also need the equation for the work done by a constant force. And so that will be our function that we take our first time derivative of. And we'll get to that a little bit later, about the importance of it, and more importantly, this dot product. Alright, so I think we have everything we need. Let's go ahead and start to solve. During our physics step, we mentioned that we're going to use the work is equal to our constant force vector dotted with our displacement vector. But you might be wondering, where does that come from? So we can take a look at this from its original form, which is work is equal to our force vector dotted with our differential position vector. And that position is going to be important because we do it from our initial position to our final position. Now, if we have an element within our integrand that is constant, what can we do? We can take it out. Good. So now we can say that our constant force vector dotted with the integral of our differential position vector from our initial to our final position. Well, the integral of our differential element is just the element itself within the confines of our initial and final position. So we take this one step further, and we have F dot our position vector from the initial to the final position. Now, what do we call it when we start from one place and go to another place? We call that displacement. So there it is. That's where the work done by a constant force is equal to our force vector dotted with our displacement vector. Alright, so let's get back to work. Now on the previous slide, we learned where our equation comes from, but we haven't discussed the big old white elephant in the room, and that's the dot product. So let's do a little exploring as to why that is. So when we talk about forces and displacement, we're actually talking about vector quantities. We can't just multiply vectors together willy-nilly. We actually only have two options: the dot product and the vector product, or you may refer to it as the cross product. The dot product produces a scalar quantity, whereas the cross product produces a vector quantity. Well, we know that work is a scalar quantity, so that's our first indication that we need to use the dot product. Our other indicator is, as I mentioned earlier, that a force only does work if it causes a displacement. In this case, our force isn't parallel to our displacement, and that's an issue, because work is only done parallel to the displacement vector. Well, the dot product takes the magnitude of one vector and multiplies the component of the second vector that is parallel to the first one. Well, that sounds a lot like what we're doing with the work done by our constant force. Well, let's look at a couple examples to kind of help bring this out. In our example, here on the left, you can see that you have a flashlight that is projecting a component of our yellow vector here onto our second vector here. And that component is parallel to the second one. Well, that's what the dot product is doing. It's taking the magnitude of the first vector and projecting it onto our second vector. And the part that is parallel to our second vector happens to be the adjacent side of this triangle we make between the two vectors. Now, if we remember our trigonometry, we have SO, CA, TOA. Now, if we're looking at the adjacent side, our little picture here already gave it away. But we're going to use the cosine of our angle between the vectors times the magnitude of our first vector. Alright, so why don't you pause the video and I want you to write out this work function in terms of our vector magnitudes in our trigonometry. So take a second, use the drawing from the draw step, and express this work function in magnitudes and angles. Alright, so hopefully you took a second to take a stab at rewriting our work function in terms of magnitudes and angle, and this should be what it should look like. So here we have our force vector and our displacement vector in black. And as I project my force vector onto my displacement vector, and I have shown that in red, I have the adjacent component, using my cosine, times the magnitude. And as I write out the work function now, I have the magnitude of my force vector times cosine of theta. So this red element right here represents the component that is parallel to my second vector, multiplied times the magnitude of my second vector. So as we write this out, we have work is equal to the magnitude of our force vector times the magnitude of our displacement vector times the cosine of the angle between our vectors. I can't highlight the importance of understanding that this angle right here is the angle between our vectors. Okay, so as we move on. We now understand where our equation came from, and we understand why we are using the dot product. Let's continue on with the next step, which is looking at the rate at which our constant force is doing work. Alright, from the previous slide, I've brought over our work function done by a constant force, displacing our object some displacement, and if there's an angle between those vectors, then I capture that information right here. And just as a reminder, here's a quick sketch of our situation. Okay, now you might be thinking, this is a work function. I need the rate at which work is being done. I wasn't given a displacement vector. I was given a velocity. Well, how can I continue? Well, lucky for us, our constant velocity means that there is no acceleration, which means that our displacement vector is going to be in the same direction as our velocity vector. Now, if you need to pause the video to think that over, go ahead. If you want to ask that question in class, please do, bring it up, but we're going to continue. Alright, so let's keep our work function as is. Now, our problem asks for the rate at which the applied force is doing work. So what can we do if we need the rate of something? Exactly, we can take the first time derivative of our work function. So we have the first time derivative of our work function, and what do we have? We have our function right here. Now as we put that into our differential form here, we have to take the derivative of this function. Uh-oh, we've got a problem, don't we? We've got a variable here, and a variable here. So what rule do we need to use in order to continue? Yes, we need to do the product rule. So if we write this all out, I want you to pause the video, use the product rule, and take the derivative of this function. Alright, so if this is what you got, then great job. If you didn't, then you may need a little more practice with your derivatives and the product rule. But again, we should have had 3 terms, and we have 3 terms because we have 3 terms in our function. For the product rule, we take one variable, leave it as the variable, and the other 2 remain constant. So we do it one at a time. For our first term, we leave our displacement and our angle constant and only take the first time derivative of our force variable. And then we do it again, except now our force variable is constant. Our displacement variable remains variable. We take the derivative of that and keep our angle constant. And then for the last one, our force and displacement variables are constant, and we take the first time derivative of our angle with respect to time, but since it's inside of our cosine function, we take the first time derivative of the whole thing. Alright, so good job. Now, I want you to think about the problem. I want you to look at each of these terms, pause the video, and figure out which ones will equal 0 and which ones stay around. Alright, so what did you discover? Well, 2 of our 3 terms are equal to 0 because our force variable is constant and our angle is constant. So here's our result. Now, here we have our derivative where it is our change in position over change in time. What does that sound like? Well, to me, it sounds a whole lot like speed. So let's rewrite it again. It is the magnitude of our force vector times our speed times the cosine of the angle between our vectors. Alright, so I call these magnitudes. Let's call them or label them as such. Alright. Now we can actually put in our given values because we have a magnitude of the force, we do have a magnitude of the velocity, which is our speed, and we have an angle. So we have our algebraic solution here. So power of our constant force is equal to 122 newtons times 5 meters per second times the cosine of 37 degrees. And that is equal to 487 watts. But this is only 2 sig figs. So we have 490 watts. Remember that watts is the same thing as joules per second, which is what we can expect for our work per time, because our work is in joules, and if we look at the rate at which work is being done, it is joules per second, and that's where these watts come in. And of course, we have our double line ANS. As we go through our check step, let's take a look. 122 newtons times 5 is, as you put it into your calculator, 610 watts, but because we're only looking at the component of our force vector that is parallel to our displacement vector, we have to take that into consideration. So our value is less than 610, and that's because the cosine of our angle is a fraction of 1, and that covers our check step. We have our proper sig figs, we have proper units, and our answer makes sense. That concludes this problem. I'll see you in class tomorrow.